Hello, welcome to our AP Chemistry Chemical Kinetics tutorial. I'm Max.
I'm Ishan.
And I'm Jordan.
Today we'll be discussing certain parts about the chemical kinetics and stuff like that. First off, we'll be discussing the factors that affect reaction rates. The more readily reactant molecules collide with one another, the more rapidly they react. Also, reactions may be classified as either homogeneous or heterogeneous. Homogeneous means that all the reactants and the products are the same states of matter, whereas heterogeneous means they're either a mix of solids, liquids, and gases. The second factor that influences reaction rate is reactant concentration. Most chemical reactions proceed more quickly if the concentrations of one or more reactants is increased. Concentration increases raise the frequency in which molecules collide, and therefore increase the rate. The third factor that increases reaction rate is reaction temperature. Reaction rates generally increase as temperatures increase. This is because increasing temperature increases the kinetic energy of the molecules during their collisions. The fourth final factor that increases reaction rate is catalysts. Catalysts increase reaction rate without being used up in reactions. They decrease the activation energy and affect the kinds of collisions in the reaction, therefore decreasing the activation energy. Now we will discuss the actual reaction rates themselves. The speed of a chemical reaction, or the reaction rate, is the change in concentration of reactants of products per unit of time. These units are generally expressed as molarity per second. Now, let's consider the hypothetical reaction A to B. At the start of the reaction, there is 1 mole of A in a 1 liter container. This means that the molarity concentration is 1 molar. After 20 seconds, the concentration of A has fallen to 0.54 molar, and the concentration of B has risen to 0.46 molar. Note that the sum of the concentrations is still 1 molar because 1 mole of B is produced by each mole of A. After 40 seconds, the concentration of A is 0.2 molar and that of B is 0.8 molar. Now consider these numbers and this information for the calculations on the next page. Also note that the rate of this reaction can be expressed as either the rate of disappearance of reactant A or as the rate of appearance of product B. Now also note for these calculations that delta, this triangle right here, means change. So in these calculations, either change of concentration or change in time, that's what delta means. Now for the average rate of appearance of B, it's simply expressed as the change in B concentration divided by the change in time. To calculate the change in concentration, you simply subtract the initial or the time 1 concentration from the final or the time 2 concentration. In this case, since it's going from 0 seconds to 20 seconds, this is considered initial, but this value can be in the middle of the reaction, as we will do later. And then to calculate the change in time, you use the same process, 1 subtracted from 2. Now, for the first 20 seconds, the rate of appearance of B is calculated as the final, which is 0.46, as described in the previous page, minus the initial, which is 0, because to start off at 0 seconds, there was no product B, divided by the final time, 20 seconds, minus the initial, 0, and you get this rate of reaction for the rate of appearance of B. Now, for the rate of disappearance of A, it's the same equation as rate of appearance of products, whereas B is our product and A is our reactant, but you must multiply the same equation by -1, because if you calculated it out using the same process, the reaction rate would be negative. And in chemistry, reaction rates are always considered positive, so that's simply to make sure that the rates are positive and the rate of disappearance is not negative, because then it becomes a double negative. So for the rate of disappearance of A, we use the final, which is 0.54 molar, minus the initial, 1, divided by 20 seconds minus 0 seconds, the same as here, and it will equal the 2.3 times 10 to the -2. Note how the two reaction rates are similar because in the original balanced equation, which we will go back to, in the original balanced equation right here, the stoichiometric ratio between the reactant and the products is 1:1. Take note of that because we will discuss that later in the video. Now, for the period of 20 seconds to 40 seconds, the calculations here are the same, except the values for the times T1 and T2 and for the concentration at time 2 and time 1, they're simply different values. But we use the same process that we did for both these, and we also used this process of multiplying by -1 for the second rate of appearance. So we simply use the 0.2 for the rate of disappearance of A minus the initial, which is, since it's at 20 seconds and our final was at 20 seconds for the first calculation, we use the same one as here, but simply here as the initial instead of the final. Divided by 40 minus 20, because our final minus our initial, equals 1.7 times 10 to the -2 milliliters per second. Now for the rate of appearance of B, 0.8 minus 0.4 divided by 40 seconds over 20 seconds equals 1.7 times 10 to the -2. And again, the rates are the same because of the 1:1 ratio of the reactants and the products. Next, we will discuss that the ratios between the reactants and the products. Now, in this reaction, we note that the ratio between the reactants and the products is 2:1, not 1:1. This means that if 2 moles of HI is reacted, it will create 1 mole of H2 or H2. So that means the rate of disappearance is twice the rate of either H2 or I2. This can be expressed as simply the rate of the HI, if we were to calculate it, simply multiply, since it's a reactant, simply multiplied by 1/2 and also a negative because it's a reactant to get the rate of the products. Now in this case, since both of these products are have the same coefficient of 1, it simply equals each other with no added coefficients. But if these were different, there would be separate numbers here, such as the 1/2. Next, we will discuss the collision model. The central idea of the collision model is that molecules must collide to react. The greater the number of collisions per second, the faster the rate. Increased temperature and reaction concentration also increases the amount and force of collisions, as discussed earlier. However, for a reaction to occur, it must be the right kind of collision as well. This means this right kind of collision takes into account the orientation factor, because even though certain molecules will hit each other, they may not be properly orientated. This means that a chemical reaction will only occur if the molecules are orientated a certain way when they collide, and if they are not, the reaction will not occur. Finally, we will discuss activation energy. This is one of the final things that must be properly aligned for a reaction to occur. It has been suggested that molecules require minimum amounts of energy to react that comes from the collision of molecules. This energy can be used to break bonds. With too little kinetic energy, molecules simply bounce off one another, and this minimum energy required is called the activation energy and is different for each reaction. That concludes our tutorial for chemical kinetics for AP Chemistry. Thank you.